Okay, we've already talked about the probability density function for a normally distributed random variable. And this is what it looked like, which seemed really obnoxious. And we actually graphed that to take a look at it by plugging in different values for mu and for sigma. And the notation that we use for a normally distributed variable is the x is distributed normally, and then you give mu the mean, comma, and then the variance, which is sigma squared. Remember, sigma is just the standard deviation. So let me make an arrow here so I can use that. All right. So this is what our curve looks like. And it turns out that with this normal curve here, that if you go one standard deviation to the left or to the right, that total area winds up being a little over 68%. And then if you go two standard deviations to the left or the right, we're going to add another almost 27% for there. So approximately 68% of the population lies between one standard deviation, and approximately 95% of the population lies between two standard deviations. And then if you go three standard deviations to the left or right of the mean, then that winds up accounting for almost all of the population, almost all of your data, 99.7%. So there's not very much after that, even though we know that we're going negative infinity to infinity, and the area under this curve winds up equaling 1. The majority of it comes within three standard deviations of your curve. All right. So let's do a few examples. The heights of young men between ages 18 and 19 follow a distribution that's approximately normal, with a mean of 181 centimeters with a standard deviation of 8 centimeters. Okay? Now, what are we going to do with that? If a man is chosen at random, find the probability that his height is within one standard deviation of the mean. Now, I just gave you the percentages and what this should wind up equaling, but let's see how we would calculate it. The probability within one standard deviation of the mean. So what we're going to do is we're going to write the integral and one standard deviation. Now, since the standard deviation is 8 and the mean is 181, if I subtract 8 from that, I get 173, so that's my lower bound. If I add 8 to the mean, I get 189. And so I'm going to do the integral from 173 to 189 of that normal distribution function. And I'm not going to be able to do that by hand, or it would take a very long time. So maybe it would be a little easier if I use my calculator. So I'm going to pull up my calculator. Let's do it over here. And I'm going to go to the distribution menu, and I'm going to do a normal CDF. And my lower is going to be 173, and my upper is 189. And then I put in the mean, which was 181, and my standard deviation, which was 8. And boom. And there's your a little more than 68% that we saw on the previous screen in that picture. So we'll say 0.683 for our answer here. Or 68.3%. Doesn't matter whichever way you want to write it. Just make sure it's clear where the decimal point is at. Okay, let's continue on with this and say, what's the probability that if a man is chosen at random that is within two standard deviations of the mean? So what would we do for that? Well, once again, we're going to do the integral. Now this time we're going to go two standard deviations, so subtract another 8 from our lower bound, and that's 165. Add another 8, that gives us 197. And then we'll grab our calculator and punch that in and see what we wind up getting. And so I'm just going to hit second enter instead of going through all the menus again. And I'll change that to 165 for the lower bound and 197 for my upper bound. And I get 95.4%, 0.954. So 0.954. 4. And these should be approximately. It's not exact. All right, so that's how we calculate it using the calculator. Once again, I believe, oops, I think we have a typo on this one. Plus or minus 2, we got, what do we get, 95.4? So this should be not 9844, that should be 9544. So you can make that correction. All right, find the probability that a randomly chosen man is at least 185 centimeters tall. So normally what you would do is think, well, I'm going to go, my lower bound is 185, and my upper bound is infinity. And that's true, that'll work, but there's a few different ways to think of it. So that's probably the most common. The probability that x is greater than or equal to 185. And so we would do that. And visually you can see what I shaded in the picture here. Let's get an arrow to point. All right, another way of thinking about it is thinking, well, it's the opposite of this area, so all I have to do is 1 or 100% minus the integral from negative infinity to 185, and that'll give me this area over here. Okay. And I mean, we can keep messing around. There's another way we could think about it, and this is kind of a crazy way to think about it, but if I think of this green area here as, well, half, so that's 50% from negative infinity to the mean, and then plus the 181 to 185, that total, half plus 181 to 185, and then subtract that from 1. Or another way to think about it is over here. We know that from 181 to infinity is 50%, so I could just subtract the integral from 181 to 185, this thin strip here, I could subtract that from 50% and get what's left here. And if I simplified this, that would wind up being 0.5 minus the integral from 181 to 185. So my point here is to realize that there's different ways of thinking about it, and there's almost always more than one way to write an integral to represent what we're looking for. So keep that in mind. Let's look at another example. A machine produces metal bolts. The length of the bolts have a normal distribution. The mean is 19.8 centimeters. Standard deviation is 0.3 centimeters. All right, so we've got our setup. If a bolt is chosen at random, find the probability that it will have a length between 20.1 and 20.7 centimeters. And then less than 19.5, greater than 19. So you might want to hit pause and try and work these out, and then hit play and see how they compare. All right, so now I'm going to work through the answers. So from 20.1 to 20.7, so we know we're doing our integral. We know our limits of integration. We know we're using the normal distribution function. And then we're going to grab our calculator and punch that in. And when you do that, you wind up getting 0.157 approximately, or 15.7%. Less than 19.5. Now this is where it gets a little interesting, so I'm going to write the integral first. So that's going to be from negative infinity to 19.5 of my function. And now let's grab the calculator and see what we get for this. All right, so negative infinity to 19.5. So I'm going to go to my distribution and do my normal CDF. Now for lower, how do I put in negative infinity? Well, I could put in a really small negative number, so I could do like negative 1 times 10 to the 99th power, something like that. And for my upper bound, 19.5. And it's the same, so my mean in this problem is 19.8. And standard deviation is 0.3. And so we get about 15.9%. So now I'm going to show you something in a second here. 15.9%. All right. so if you look at it, the standard deviation is only 0.3. And remember, the probability that something lies within 3 standard deviations of the mean is almost 100%. It's 99 point something percent. So 3 standard deviations would be 0.9, or just about 1 unit. So my answer is not going to be too far off if I don't go all the way to negative infinity. So watch what I'm going to do here. I'm going to do the normal CDF. Instead of negative 1 times 10 to the 99th, how about I just go, let's say, 2 units below 19.5. So what if I put in 17.5? Let's see how much that's off from our previous answer. Oh gosh, it's exactly the same. Because I only went 2 standard deviations to the left of the mean. I didn't have to go to negative infinity, but we know that just going I went 6 standard deviations to the left. And we know that if we go 3 standard deviations to the left, that's going to account for most of our data. Let me go back to that picture, which was over here, I believe. Yeah. So notice there's 1, 2, 3 standard deviations here. That accounts for 99.7%. And so I actually just went 6 standard deviations over. And so the amount of area from there to my upper limit wound up being almost exactly the same as if I had gone way down to negative infinity, or as close to negative infinity as possible. So keep that in mind. You don't have to worry about typing in a gigantic number. Just figure out what is your mean, and then what is the standard deviation. And then if you go more than 3 standard deviations left or right, you should be okay. All right, let's do the last one. Let's find the probability that it's greater than 19. So once again, this is going to be the integral from 19 to infinity, but I don't have to punch in infinity as I just explained. And so, let's see, how about I punch in, let's clear that so it doesn't confuse you, normal CDF. So we're going from 19, and upper limit, oh, I don't know, I could punch in something like 22 and I should be fine. If I want to be safe, I can plug in something a little bit bigger. We'll say like 25. And we get 99.6%, so 0.996. And you can mess around with putting in other numbers instead of negative infinity, positive infinity, and seeing when it actually does start to be a little different with your, usually it's going to go several significant digits down. All right, let's look at one last example. The time it's taken by students to complete a puzzle is normally distributed with a mean of 28.3 minutes. Standard deviation, a little over 3.5 minutes, 3.6 minutes. Calculate the probability that a randomly selected student took at least 30 minutes to complete. All right, so once again, you might want to hit pause, work this out, get an answer, and then hit play and see how you compare. So at least 30 minutes. That means I'm going to go from 30 to infinity, although I'm guessing they're not going to let students keep taking the test forever. There's probably a cutoff somewhere, right? F of x dx. And then I'll grab my calculator. So let's see, my mean was 28.3, standard deviation 3.6. So grab the calculator, clear second, bars 2. All right, so my lower is 30. My upper, I don't want to think too hard, I'm just going to throw in 100. My mean was 28.3, and standard deviation was 3.6. So 3 standard deviations here would be, what, 10.8, so almost a little less than 11. And I put in an upper for 100, so I know I'm covered if I only have to worry about 3 decimal places. And so I get 31.8 approximately. Now, I actually want to store this. So I'm going to store this into, I don't know, Let's store this into S. You'll see why in a minute. Okay, so now I've got that complete decimal stored in S. So 3.318. Let me write my answer here. All right, now look at the next question. Out of 10 randomly selected students, find the probability that at most half of them took at least 30 minutes to complete. So now this has switched. And did you recognize this as a binomial? And so the success is going to be if it takes at least 30 minutes, and then not success or failure would be it took less than 30 minutes. So I'm going to let S represent the probability that it took at least 30 minutes. And we know from the first part of this problem that's 0.318. Oh, that's why he stored that number. And then I'll have N for not success. That'll be the probability that X is less than 30, which would be 1 minus 0.318. All right, so now I want to set up a binomial for this. I don't need to look at that other part now. I've got the 0.318 set up. So if I want to set up a binomial for this, I'm going to be doing S plus N, and we had 10 randomly selected students. So each student, the probability is the same. One doesn't affect the other, so I've set it up as a binomial, and they want to know what's the probability at most half of them. So that means that none of them, and then that would be N to the 10th, or plus one of them, or two of them, or three of them, or four of them, or five of them, and then I'm going to stop there. So I'm going to stop at 10, choose 5, S to the 5th, N to the 5th. And so those are the only ones I'm interested in. And we talked about how you can do this. We could do it by hand, but then we're still going to have to grab our calculator with that 0.318 number, because it's not a number that's simple that we can plug in like a fraction or a terminating decimal. So I'm going to use my calculator either way, or we can do the cumulative. And so let's go ahead and grab our calculator. Now I stored that 0.318 number in S, so clear. So I'm going to go back to my distribution menu, second vars, and I'm going to go all the way down to binomial CDF, and I have 10 trials. The probability, now I'm going to put alpha S in there. And this, remember how the binomial CDF works, it adds up from 0 up until the X value you plug in. So I'm going to plug in 5. And so I get 93.8% approximately. So 0.938. So we're tying together ideas that we learned before with these new ideas with normal distribution. And that's it.